Okay, the speed of DC motor is controlled by a PI controlling system. Okay, so this is the block diagram for this PI controlling, and this is the proportional coefficient Kp, and this is the integration coefficient Ki, and this is the integration 1 over S. Okay, and this is a P controlling, this is the integration controlling. Okay, and this is the modeling. The Kp can be calculated as this 3.4 equation, and the integration coefficient can be calculated this, okay, 3.5. The K and tau are the parameters we measured in the previous controller modeling part, okay. And over here you can see in the default setting, when the input is 25 rad per second, frequency 0.4, offset 100, and also the control parameters as Kp as 0.05, Ki as 1. Okay, so the simulated result, which is the square waveform, is almost matching as the actual measurement of the DC motor speed. Okay, so basically the same thing. And over here we can see in lab 1 it's basically the same configuration, and what we need to do is to examine the behavior of the measure speed as showing red, and also the reference speed showing blue. Okay, so the reference is the simulated one, and the red one is the actual measurement. So you can see in speed control, you can see it's spinning at a different speed. Okay, sometimes it goes quicker and sometimes it goes slower. And then now let me do the experiment over here. So increment or decrement the Kp by 0.005. So if I just simply click the Kp over here, the arrow over here, it will change the values. Okay, and if we continuously changing the values to a higher value, you can see the waveform has some difference in compared to the previous result. Okay, so you need to figure out what goes different, and in 7 look at the changes of the measure signal with respect to the reference signal, and explain the performance difference of changing Kp. And if I simply set Kp to 0, oops, Ki to 0 as well, oops, let me stop it first and redo it, and you will see there's no actual measurement of the DC motor, and the DC motor is stopped spinning. Okay, and increment the Ki in steps of 0.05 like this, and you'll see it's over damping waveform. Okay, and if you increase it a little bit, it will somehow show a little bit not that much over under damping. Okay, and if we continually increase it, you'll see the signal is performing under damping. Okay, and then and once you reach at a certain point, the signal starts to oscillating. Okay, and what you need to do is to increase this a little bit to reduce the damping ratio. Okay, and to figure out the exact Kp and Ki to make it more consistent with the simulated or the reference waveform. Okay, so this is for part 1. And part 2, given these two parameters, zeta and omega 0, you can compute the Kp and Ki by using the equations over here, 3.4 and 3.5, together with the parameters you measured in the last experiment, K and tau, and do the calculations and see what the numbers of these Kp and Ki are. Okay, and for the third one,